Hello everyone, I'm Jasper. I hope to show you how to load a pre-trained latent terrain model into Max MSP. So make sure that we have the autoencoder and autoencoder external installed correctly. If you haven't done so, make sure to follow the instruction at the download and installation page. And if you have done so, we can go to the pre-trained terrain page. And here you can see that it listed some of the pre-trained terrain to get started and their corresponding autoencoders. We'll be using the Rave model, which is an autoencoder developed by Axid Aircam. We'll be using the one called Percussion, so make sure that you have grabbed the Rave model from this link and also download the terrain model from here, the first one, the demo. We're just going to make sure that our Max MSP is able to find these files. We can do that by going into Options, File Preferences, and make sure that our file is in one of these folders. So if you have used Rave in Max MSP before, this shouldn't look very unfamiliar to you because this is a pretty standard encoder and decoder architecture. We have the encoder to compress audio waveform into what we call a latent space. And in this case, we have a 4-channel latent signal. Then we have the decoder to hopefully reconstruct the original audio signal like this. And if you keep the decoder only, by manually controlling this 4 latent signal, in that case, we'll get a pretty nice deep learning audio synthesizer like this. In this case, it's kind of alright because we only have 4 latent dimensions. It's still in kind of a manageable amount. But for some of the autoencoders, this number can go up very quickly to something like 64. It's not that easy to manage anymore. So the latent terrain system is designed for this. It aims to use a very low dimensional control signal to produce high dimensional latent signals. So we'll go back to the basic Rave example and delete the encoder because it's a decoder only approach and we also don't need this anymore. So first of all, we will need to create an autoencoder object, autoencoder.terrain. Here we're just going to type in the file name, which was percussion terrain demo. I'm just going to copy and paste that. And you see that it's giving us 6 outlets in total. The first 4 of them will be the latent signal. So we'll connect them to our decoder. And we can also add a autoencoder GUI, graphic user interface object. And this will be our basic X and Y trackpad. So it's a 2-dimensional X and Y system. We also need to set the behavior in this UI tasks section from dataset to stylus. So we can just use that as a, stylus. And you can see that the second to last outlet will give us the current X and Y location of our mouse. And if you're using a stylus on the tablet, that will also give you the pen pressure. I'm not using one right now, so I'm just going to use the first 2. I'll unpack them into 2 floating numbers, which is X and Y. And you can see that now this is a centralized coordinate, which means that if we move our mouse closer to the center, and that will give us something closer to the origin. So we'll convert the floating number to signals. We can do that using the sig object. And I'm just going to clear up the space a little bit. So this would be the input for our terrain model, X and Y. And just for the sake of visualization, we can add a multi-slider with a size of 4 so that we can kind of visualize our latent vector produced by the terrain. And then set the range to -5 to 5, which is a pretty standard range of a latent space. And then we'll use mc.pack with 4 channels, and that will take the latent vector we have produced, followed by a mc.snapshot to convert our latent signal to latent numbers, and that should happen at a rate of 20 milliseconds, and we have 4 channels. And then we just need a zl.group, so that will convert our floating numbers into a group of 4, which is the dimension of our latent space. Alright, so now if I go to the inspector, I can enable the terrain model and also enable the rave model, the decoder as well here. Now if I start DSP, you can see you see that it's only taking the X and Y and map that into a relatively complex latent signal. So that's a quite basic workflow. What we can do now is we can actually visualize how our terrain looks like. So we can do that by using the message plot interval. So because the terrain, the input space, is a closed finite interval, so we can basically sample all of the pixels in this canvas and then visualize one of the latent dimension that will turn into a visualization. So that's what plot interval is for. So we'll need to specify the range in X and Y. We can do that by going back to the GUI, the inspector. You see the value boundaries, which give us the value at left top, right bottom. So I'm just going to copy and paste that set of number here. And we also need to specify the X and Y resolutions. So we can go to the patching rectangle, and the last 2 digit is what we're looking for. I'm going to paste that here as well. And just a side note, if you're using a pre-release of Unknown Terrain, the beta version, will get a slightly different behavior. I do apologize for that. Just double check the documentation or to grab the latest version of Unknown Terrain. So we'll send the message to Unknown Terrain, and the second to last outlet will produce the plotted interval as a dictionary, which is going to directly connect that to the GUI, like this. So now if I press the message, you see that will give us this grayscale visualization of our terrain. This is like looking at the terrain from the top, from up to down. So if it's a brighter region, and that will indicate one of the latent value here is higher. So usually for rave, this kind of gives you a indication of the amplitude of the sound it gives you, but that is, I guess, just for rave. Right, so that is a basic workflow of loading a terrain and use that with an autoencoder. So in the next video, we'll talk about how to actually build a terrain from scratch. So thanks for watching, and I'll see you next time.